The next topic we'll be addressing is called orbitals and the term quantum numbers. And I just wanted to spend a few minutes kind of making sure I go back and kind of bring us up to speed one more time. Some of those topics that we've been dealing with might seem just so abstract, and I just wanted to be sure we take a moment and really consider where we're starting and where we've been. Now I know the new note pack is opened up to page 10 and I see quantum numbers, but let me just backtrack a little before we jump into the new lesson and be sure, I'm just reminding us where we've been along the journey in terms of what's called the quantum mechanical model. So a little review, a little time for me to just kind of review with you some of the key concepts we've covered. I remember opening up our lesson and talking about the evolution of the atomic theory. What did we once believe an atom to look like, all the way up to our current modern model known as the quantum mechanical model? And we started with John Dalton, first page of your note pack. John Dalton gave us very specific ideas that an atom was an indivisible building block of matter. Think of it as just a solid mass. No such thing as subatomic particles such as protons, neutrons, or electrons. A solid mass, indivisible in nature. Atoms came together to create larger structures known as compounds. Dalton laid the foundation of a lot of good chemistry. But as our technology increased, the ability to experiment, we started to expand the notion of what atoms truly looked like. And we talked about the Thomson model, good old J.J. Thomson. Now it was called a plum pudding model, if you remember from the earlier notes, but I had a hard time thinking about what plum pudding looked like, so I called it a chocolate chip cookie. Think about this particular picture modeling a chocolate chip cookie, where we have this positive dough with electrons scattered throughout. In the 19th century, Thomas described the atom as a ball of positive charge containing a number of electrons. Absolutely no idea how electrons were arranged. They were just randomly dispersed through a positive dough. But then Rutherford came along and conducted many experiments, famous one called the gold foil experiment. If you ever should get a chance in YouTube, Rutherford's gold foil experiment, it's quite interesting to see how he actually conducted with alpha particles, a radioactive particle. And through that experiment, he concluded that in the center of an atom is this tiny, tiny region, very, very dense, known as the nucleus. And that nucleus contains the positive beings he called protons. So moving from a random dispersion to a very central core of positive and neutral, protons and neutrons are what they're referred to now, known as the nucleus. But the vast majority of the atom was empty space, because those electrons were so tiny compared to the size of protons and neutrons. They appeared to be empty space. But notice with the Rutherford model, no organization to the electrons. Niels Bohr contributed the arrangement known as the solar system. He actually said electrons reside in specific energy levels. If you've ever drawn a model where we draw one ring and place 2 electrons in it, the second ring can hold up to 8 electrons. You have been drawing a solar system model, or sometimes known as the planetary model. That really is Niels Bohr contribution, organizing the electrons in very discrete energy levels. This solar system model is still taught today, and it works great for a lot of predictions. Friends, it's just not what an atom truly looks like. And we've been spending a great deal of time trying to bring ourselves up to speed, moving from a planetary model to the current model known as the quantum mechanical model, our modern atomic theory describing electronic structure of the atom as the probability of finding electrons within certain regions of space. Notice now I've gone from pretty much a planetary model where I can see discrete energy levels to a complete electron cloud. We even talked about Heisenberg, his uncertainty principle. In the last lesson I mentioned Heisenberg.
Because an electron is so small, it behaves more like an energy packet, an actual wave traveling with a certain wavelength and a certain frequency as any other wave particle would do. Light travels as photons, a particle-wave duality of nature. Electrons do the same thing. And since electrons behave as waves, we study them as a crossover with our physics topic. Because electrons travel as waves, we spent some time talking about the speed of light is equal to the wavelength times the frequency. And I can actually calculate how the certain wavelength or the frequency of an electron given a certain amount of energy. We calculated wavelength using Planck's constant. This is known as the de Broglie equation, where the mass of the electron, measured in a kilogram, times the velocity of that electron set out underneath Planck's constant. Remember, mass times velocity was known as momentum. So I can use these two relationships to solve literally for wavelength or frequency or energy content in a specific for a specific electron. And all of that was reviewed for us, thinking about the other relationship here. If I wanted to mention energy, that was Planck's constant times the frequency as well. You know, my V might look like a nu for wavelength. So the nu is a squiggly V for the frequency. Mass times velocity is underneath my de Broglie equation. Energy measured in joule, Planck's constant, and the frequency is one relationship. De Broglie equation said wavelength can be calculated using Planck's constant set over the momentum, mass measured in kilogram times velocity. And of course, the speed of light constant is used with the inverse relationship of wavelength and frequency. All of those equations have been coming up again and again as just practice, and I just wanted to stress why. Electrons don't look like a solar system around the atom. They behave as waves, and these waves take certain shapes to them. This particular model is showing what I'd call an S-shaped cloud. But let's take a moment and review all the shapes of the clouds. We drew these into our notes earlier. Oh, this is printed backwards. The S-shaped orbital is a spherical shaped orbital on an XYZ axis. The P-shaped orbitals, Px, Py, Pz, based on a three-dimensional axis, have three different orbitals, three different ways those electrons can orientate themselves around an XYZ axis. And if I just overlay an S orbital with a Px, Py, Pz orbital all on the same set of axes, look what it starts to look like. I have a center S, I have a Px, Py, Pz. That's what an electron cloud looks like as I start to build atoms and show where those electrons reside in these areas of probability known as electron clouds. Not rings around a nucleus like a planet model, but different shaped clouds. And we even talked about the clouds getting more and more complex in shape. The 5 different orientations in space for the D, and I didn't ask you to draw because they're pretty complex, but the 7 different spatial orientations for the F orbitals. Electrons live in orbitals that surround the nucleus, and that allows me to bring up to speed today's new lesson on quantum numbers. All of that was so that I could just ramble a little bit, giving you a description of what quantum numbers are telling us. Every electron in an atom has an address that's unique to that specific electron. If I live in a certain house, I have house numbers. On a street, my street has a name. I live in a city with a state and a zip code. That is a great analogy of what quantum numbers do for the electrons in an atom. The 4 quantum numbers, and there's 4 of them, that give me a very, very specific address for an electron around the nucleus of an atom. And just as you and I have different addresses, we might live in the same state. We do. We might live in the same city. Most likely we do. Heck, we might live in the same road, on the same road, but I can guarantee you we do not have the same address on that road, not that I'm aware of. By the time we get that specific, street number with the road name, the city, and the state, I have given you 4 pieces of information that make my address different from your address. That's the purpose of a quantum number, giving an address to every electron in an atom that makes it unique from any other electron in that atom. So today's topic, giving addresses, giving a unique set of 4 numbers called quantum numbers to a single electron's position within the atom. It's analogous. It's the same as giving our homes a single unique address to represent its location. So let's talk about, first of all, the principal quantum number denoted with the letter N. The principal quantum number denoted with the letter N. The size and the energy of the orbital. N has integers always greater than 0. Now, let me give this context. Principal quantum number N tells me the size and the energy of an orbital. Principal quantum number N tells me the size and energy of an orbital. N always has numbers, whole numbers, integers, greater than 0. Now let's revisit what this means. Remember our pyramid, the electron pyramid? Principal energy levels are denoted by the number, the large number out front. N equal 1, that is my first energy level. N equals 2 is the second energy level. If N equals 3, it's the third energy level. N equals 4, and so forth. The rows going across, indicated by the large number placed in front of the sublevel, give me the principal energy level. The principal energy level 1 has 1 sublevel, an S-shaped cloud. Principal energy level 2 has 2 sublevels, the S and the P-shaped clouds. Principal energy level 3 has 3 sublevels, S, P, and D-shaped clouds, and so forth. Principal energy levels are always whole numbers greater than 0. And remember, when I'm looking at the periodic table, I can indicate the principal energy level from the period it lives in. The period is going to tell me how many rings we would place around the nucleus in the old Bohr model, the planetary system. And that still holds true today, even in the quantum mechanical model. Principal quantum number N is the whole number telling me how far away the nucleus is, or excuse me, the electrons are from the nucleus. Principal energy level 1 is the closest to the nucleus. Principal energy level 2 is the next closest to the nucleus. Principal energy level 3 is a little further out from energy level 2, and so forth. The size and the energy. The farther out it is, the higher energy it possesses. The farther out it is, the larger the size. Closest to the nucleus is the lowest energy. Principal quantum number N. Now, let's take a look at the second of the 4 quantum numbers. Our text lists it as the azimuthal quantum number, and that is a cursive L. That's the best I could do to type it. The azimuthal quantum number. Now, other chemistry books I've seen have called it the angular momentum quantum number. Maybe we should write down both so we're aware that it has 2 names. The azimuthal quantum number, or the angular momentum quantum number. Now, in the next series, What we're giving now is a number to the shape of the cloud. Remember, when I was just looking at this, principal quantum number n is 1, and I called this a sublevel. Well, that S-shaped cloud needs a number, because that's what addresses are. They're numbers. I need to give a number for the S-shaped cloud. I need to give a number to the P-shaped cloud. I need to give a number to the D-shaped cloud and to the F-shaped cloud, because these are called quantum numbers. Now that might seem silly. Why don't I just say the S cloud, the P cloud, the D cloud, the F cloud? Because when we say quantum numbers, these will be a series of 4 numbers that we have to envision as an address. So here's what we've done. The letter S, representing a spherical shaped cloud, now is designated with a value of L as 0. If I see the number 1 for the azimuthal quantum number, I now know they're referring to a P. The number 2 is the D-shaped cloud, and the letter F represents the third value of L. Let me put this up. The angular momentum, or azimuthal quantum number, a cursive L, is telling me the shape of the orbital. Is it an S-shaped, P-shaped, D-shaped, or an F-shaped cloud? The shape of the orbital. Now remember, the first one, principal energy level, N. N tells me how far away from the nucleus it is, the energy, and the size. Now, the L is telling me the shape. If the shape is an S-shaped, L equals 0. If the shape is a P-shaped cloud, L is equal to 1. D is designated with a 2, F is designated as a 3, G is designated as a 4, and again we could keep going, but we don't have that large of atoms on our periodic table to go any further. Another important note on this slide, the angular momentum or azimuthal quantum number L always has values of 0 to n minus 1. 0 to n minus 1. Now let's make sense of that. In the first energy level, n equals 1. Principal quantum number, n equal 1. What are all the possible values for L? L is always 0 to n minus 1. What is n minus 1? Well, if I'm in the first energy level, 1 minus 1 is 0. All the numbers from 0 to 0. So all the numbers of 0 to 0, that's one number. That's the number 0. What is the only shape we see in the first energy level? Well, that's the shape with the value of 0. It's an S-shaped cloud. If n is equal to 1, there's one sublevel. If n is equal to 1, all the numbers from 0 to 0 are the S-shaped cloud only. Let's try another. What if n is equal to 3? If n is equal to 3, this is the third energy level. L has a value of all the numbers from 0 to n minus 1. All the numbers from 0 to n minus 1 would include a 0, a 1, and a 2. What are the shapes that we find in the third energy level? We find the S, the P, and the D-shaped clouds. Notice that those are the very numbers, a 0, a 1, and a 2, 0, 1, 2, that we assigned for the third energy level. There are 3 sublevels. 0, I have to think S-shaped. 1, I think a P-shaped cloud. And 2, I think a D-shaped cloud. 3 sublevels in the third principal energy level, an S, a P, and a D. The third quantum number is called the magnetic quantum number, m sub L. M sub L, and that's the same cursive L. The magnetic quantum number. These are given integer values between negative L and positive L, including the number 0. What this number is designed to do is to describe the orientation of the orbital in space. The orientation for the orbital in space. The magnetic quantum number, m sub L, is given integers from negative L to positive L, including 0. It's telling me about the orientation in space of that specific orbital. Now, let me try to help visualize what I'm saying, and I'll put a picture back up. This is the same diagram I had up, just kind of showing visually an S-shaped cloud, the P-shaped cloud, and then the overlay. If this is an S orbital, and it is, even though it came off the copier backwards, like a mirror image, S orbital, we see that there is one spatial orientation for this orbital. Remember the value for S was given 0. The L, just toss that, the L quantum number, if it's 0, is assigned the S-shaped cloud. Alrighty. So what are all the numbers if L indicates an S-shaped cloud assigned a number 0? What are all the numbers from 0 to 0? Well, that's again 0. How many numbers did we write? We wrote a single number, the number 0. M sub L is also 0 for the S-shaped cloud. S has one spatial orientation assigned the number 0 for the m sub L, the magnetic quantum number. You probably should sketch this. It might get tricky. Sketch it with me as we're drawing. One spatial orientation. Now, keep in mind, n, the principal quantum number, could be 1, 2, 3, 4, 5, 6, or 7. Any of those principal energy levels have an S-shaped cloud. So n could be the number 1, the number 2, the number 3. But as soon as I assign L the value of 0, I'm now telling you it's an S-shaped cloud. And anytime I'm telling you it's an S-shaped cloud, I'm also telling you the m sub L value has to be 0. It has just one spatial orientation. We write a single number to denote that. Suppose we're looking at p orbitals. The azimuthal or angular momentum quantum number L that denotes the p-shaped orbital was the number 1. As soon as I'm assigning L, the angular momentum or azimuthal quantum number, the value 1, I'm letting you know it's a p-shaped cloud. If m sub L, the magnetic quantum number, which is describing the orientation of the orbital in space, has the values of negative L to positive L, and if L is 1, we have a negative 1, a 0, and a positive 1. How many different numbers did we write? We wrote 3, a negative 1, a 0, and a 1. How many spatial orientations does a p-shaped cloud have? Well, it has 3. P sub x could be denoted with a negative 1 for the m sub L. P sub y could be denoted with a 0, and P sub z could be denoted with a positive 1. What we're giving is a unique number to each one of the unique spatial orientations. The s orbital has a single number, the spatial orientation assigned as 0. The p-shaped cloud has 3 spatial orientations, a negative 1, a 0, and a positive 1. What about the d sublevel? Recall how the d sublevel had an azimuthal quantum number assigned the value of 2. If L equals 2, m sub L are all the numbers between negative L and positive L, which is negative 2, negative 1, 0, positive 1, positive 2. How many different numbers did we write? 1, 2, 3, 4, 5. We've written 5 numbers to give a number as an address to each of the 5 spatial orientations that the D sublevel could obtain. So the D sub xy, D sub xz, and so forth have now been differentiated by giving an M sub L address to each of the 5 unique ways that they orientate themselves in shape. The last of our quantum numbers is called the spin number. Now remember, we learned that at most any orbital can have up to 2 electrons. They have to have an opposite spin, and that's the designation of the last quantum number, called the electron spin quantum number, M sub s. The M sub s can have 2 values, a positive 1/2 if it's spinning up, or a negative 1/2 if it's spinning down. If the electron is spinning up, give it a positive 1/2. If the electron is spinning down, give it a negative 1/2. What I'm referring to is when we were drawing orbital diagrams, at most 2 electrons can live in the same address, but they have to have a unique final number, a spin up or a spin down. There's the rule. No 2 electrons in an atom can have the same set of 4 quantum numbers. Oh, they can live in this orbital. Let's say I can have an electron in a 1s orbital up to 2, but that final set of address information is going to make 1 spin up, 1 spin down. Oh, I can have up to 2 electrons in the P sub x in the second energy level, but 1 better spin up, 1 better spin down to finally give it a unique set of 4 quantum numbers. The magnetic spin is either positive or negative 1/2. Absolutely doesn't matter if you make an electron spin up or spin down, just that they're all parallel as you go through. Let's practice with some review questions, some of the concepts here, wrapping up our quantum number lesson with examples, trying to help clarify what the addresses of electrons look like. If n is equal to 4, what are the possible values of L? The L is the azimuthal or angular momentum. It's telling us the shape of the cloud. If n is equal to 4, that refers to the 4th principal energy level. I'm counting 4 sublevels, an S, a P, a D, and an F-shaped cloud. Those 4 sublevels are given numbers, a 0, a 1, a 2, and a 3. If n is equal to 4, the rule says that L will be all the numbers from 0 to n minus 1. 4 minus 1 brings me to 3. All the numbers between 0 and 3 include a 0, a 1, a 2, and a 3. In the 4th principal energy level, we'd have an S, denoted by a 0. We'd have a P, denoted by the number 1. We'd have a D, denoted by the number 2. And we'd have a F, denoted by the number 3. The 4th principal energy level has 4 sublevels, an S, P, D, F, which are given angular momentum quantum number values of 0, 1, 2, 3, respectively. Number 2. If L is equal to 2, keep in mind, if L is equal to 2, they're referring to a D-shaped cloud, aren't they? What are the possible values of M sub L? Remember, M sub L are the integers from negative L to positive L. So let's make sense of that. L is equal to 2. So all the numbers between negative L and positive L. Well, let's show that visually. If L is equal to 2, what shaped cloud is that? Well, you're right, it's a D-shaped cloud. When we drew a D-shaped cloud, let me find it. Thank you. Here it is. A D-shaped cloud. We assigned M sub L quantum numbers to denote the 5 spatial orientations. It's like thinking of bedrooms in a house, houses on a street. Every house on a street has a different designation. -2, -1, 0, 1, and 2, representing the 5 possible shapes of a D-shaped orbital. When L is equal to 2, M sub L has the values of -2, this shape, -1, this shape, 0, 1, and 2 shaped clouds. 5 spatial orientations for the 5 numbers on the number line between -2 and +2. How many possible values for L and M sub L are there when n equals 3? We're in the third energy level. Third energy level, that's what N stands for. The third energy level has a 3s, a 3p, and a 3d. So let's put that into quantum numbers. If n is equal to 3, L are all the numbers from 0 to n minus 1. All the numbers from 0 to n minus 1. 0 represents an S-shaped cloud. P is the number 1, and the number 2 gives me the D-shaped cloud. And that's what we looked at. The third energy level, there's an S, a P, and a D-shaped cloud, given the L values of 0, 1, and 2, assigning a number to the shape of the cloud. Well, now, a little more work involved. If L is equal to 0, the value of M sub L, let's see if I can find that picture. If L is equal to 0, we're referring to the S-shaped cloud. How many spatial orientations are there? Well, there's one. One spatial orientation for an S-shaped cloud, and it's given the M sub L value of 0. So L is 0, M sub L is also 0. What if I have L equal to 1? L equal to 1 is indicating a P-shaped cloud. What are the values for M sub L? -1, 0, and +1. There are 3 spatial orientations for a P-shaped cloud. Those 3 spatial orientations are given numbers, a -1, a 0, and a +1. We had one more to look at. In the third energy level, in the D sublevel, where L is equal to 2, right? L is equal to 2 for the letter D, the D-shaped cloud, M sub L would have the value of -2, -1, 0, 1, 2. There are 5 spatial orientations, but visually we saw that. 5 spatial orientations for the D-shaped cloud. The M sub L is giving a unique address to each of those spatial orientations. If n is equal to 5, the 5th energy level, keep in mind on our electron configuration, there's actually a 5G, but we never have electrons ever make it that far. Notice how we're adding 4 each and every time, so it would be an 18, would be the superscript. But the 5th energy level has 5 sublevels, a 0, 1, 2, 3, 4, the number 4 given to the D, the G sublevel. So if n is equal to 5, L is equal to 0, 1, 2, 3, and 4. I think I had a slide earlier that placed the G sublevel on there. L is 0 for S, 1 for P, 2 for Ds, 3 for Fs, 4 for Gs. Friends, we have no atoms that large, but keep in mind the rules. The number of sublevels always matches the principal energy level. If n is equal to 5, I must have 5 sublevels. 1, 2, 3, 4, 5. Even if we don't have atoms that large, we make up these letters, pretty much. 5 sublevels. S is denoted with a 0, P is denoted with a 1, D's with a 2, F 3, G's 4. 5 sublevels, 0 to the number 4. If L is equal to 0, M sub L is 0. Same answer. If L is equal to 1, M sub L, negative 1, 0, and 1. If L is equal to 2, negative 2, negative 1, 0, 1, and 2. So this part works for both A and B. We just have to add on. What if L is equal to 3? M sub L, negative 3, negative 2, negative 1, 0, 1, 2, 3. How many numbers? 1, 2, 3, 4, 5, 6, 7. 7 numbers to remind me that there's 7 spatial orientations for the F sublevel. If L is equal to 4, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. There are 9 spatial orientations, giving us a total of up to 18 electrons, as we had predicted by following that trend. The G-shaped clouds have 9 spatial orientations, each one holding up to 2 electrons for a maximum of 18. Let's try one more in our video. Give the numerical value of N and L corresponding to each of the following designations. 3p. N is equal to 3 and L is equal to 1, the P-shaped cloud in the third energy level. 2s, N is equal to 2, L is equal to 0. 4f, N is equal to 4, L is equal to 3. N equal 5, the sublevel D given a value of 2. The purpose of quantum numbers is to assign addresses to every electron. Perhaps I'd like to close before we go on to the next brand new lesson. I want to close by thinking about an example you might run across in a practice test, a set of homework, or certainly on your multiple choice. Let me take an element such as fluorine, not something so large, but just to practice. Fluorine is number 9 on our periodic table. If I were to write out the electron configuration for 9 electrons, 1s2, 2s2, 2p5 gets me to 9 electrons. Fluorine is in the second period, the p5 column. The last thing I would write would be 2p5. 1s2, 2s2, 2p5. And I'm doing this kind of in a strange way on purpose so I can write out the quantum numbers. Keep in mind, the first energy level in the S sublevel holds 2 electrons, one spinning up, one spinning down. The second energy level has 2 sublevels, an S and a P. In the S sublevel, there's 2 electrons spinning up, spinning down. There's 5 more electrons in the P sublevel. The second energy level has 7 electrons altogether, 2 in the S, 5 more in the P, for a total of 7 electrons in the outermost energy level, N equal 2. But there are indeed 7 unique electrons. Every one of those electrons has a unique address. Let's write for the first electron. What are the 4 quantum numbers for electron number 1? When I say electron number 1, I'm going to say this guy. N equal 1, first energy level. L equal 0, it's an S-shaped cloud. M sub L is also 0, just one spatial orientation. M sub S, the spin number, it's spinning up, so I'm going to make that a positive 1/2. There is the 4 set of numbers for my first electron. But there's a second electron. Let's write its address using the 4 quantum numbers. It also is in the first energy level. It also is in the S sublevel. It has the same spatial orientation, but finally, what makes its address unique is that it's spinning down. It shares 3 of the 4 quantum numbers in common. It's the 4th one that makes it unique. One spins up, one spins down. Let's keep going. Electron number 3. Let's write out its 4 quantum numbers. By number 3, I'm referring to the up arrow in the S sublevel. N is 2. L is also a S-shaped cloud, making its M sub L 0. And since it's spinning up, I'll assign it a positive 1/2. The 4 quantum numbers: the energy level, the shape of the cloud, the spatial orientation, followed by the spin. Electron number 4. It lives in the same energy level, same spatial orientation, S-shaped cloud, M sub L also 0, but finally it is spinning down, a negative 1/2 spin number. Notice that every electron has a unique set of 4. We have to keep going. Electron number 5. By electron number 5, I'm going to assign that to this arrow. Now remember, the P's have 3 spatial orientations. We're still in the second energy level, but now we're in a P-shaped cloud. L is equal to 1 for the P-shaped cloud. M sub L are all the numbers between -1 and +1. -1, 0. I'm sorry, -1, 0, and +1. So let's denote those 3 different spatial orientations with an M sub L quantum number. And again, I'll just point to this guy first. I'll say he's in the -1 spatial orientation. His spin is up, positive 1/2. Notice the rules say that we place 1 electron into each orbital first. So electron 6 has to be in the next spatial orientation with the same spin. N is equal to 2, L is equal to 1, but M sub L is now 0, spinning the same way with a positive value. Electron number 7. Electron 7 lives in the second energy level, in the P-shaped cloud, but the spatial orientation is now the positive 1 spatial orientation. It is also spinning up. Notice I have 3 positive 1/2 spins. Place 1 into each electron first, or into each orbital first. Finally, we go back and give partners. Electron 8, N is equal to 2. Second energy level, in the P sublevel. The spatial orientation back to the -1 designation, and now it's spinning down. -1/2 is its value. Electron number 9. The last and final electron to place is this guy. Same energy level, same shaped cloud, but now the spatial orientation has gone back to the 0, spinning down. 3 spatial orientations for the P orbital. Those 3 spatial orientations we had just denoted with a, let me see if I can pull it out, -1, 0, and +1, px, py, pz, given a quantum number. The 9 electrons for fluorine, each one of the 4 quantum numbers designated for each one of those 9 electrons gives a home to each one of those 9 electrons, a unique set of 4 numbers giving a unique address. Back to the analogy where I have a street number, on my house, on a certain street, in a city, in a state. same idea. Energy level, principal energy level N. The shape of the cloud, L. The orientation of that cloud in space, m sub L. And finally, the spin number. Is it spinning up or spinning down? You have plenty of practice to start some recommended homework problems to kind of solidify these skills. See how the multiple choice is feeling as well if you need to look up parallel problems. Quantum numbers, I think, are a practice skill. Once you get them practiced, kids have told me in the past that they actually are quite easy, but rough at first. So I just want to encourage you to keep practicing. When you've mastered this skill, you're ready for the next video lesson on periodic trends.